Today's background is from a folder that I call the Sunrise subset as a bit of a sort of pun on sunrise sunset. And it's the folder that's got all of my photos that are taken within an hour of sunrise and an hour of sunset, just to get that magic light that you get in photographs at those times of the day. And so it's just a roadside shot from a little town called Yanco that's on the road between Narrandera and Leeton in southwest New South Wales. And it's a nice little area to drive through. It's quite green. Most of your fruit and food crops get grown there, so you can drive along the highway down there. And on one side of the road, you've got oranges. On the other side of the road, you've got grapes. You go a little bit further down, there's some other interesting crop growing. And it's just really nice to sort of get out there and see where your food is coming from. So in this second half, what I want to do is come back to my quantum spin problem in an arbitrary direction. And now that we've got the eigenvectors and eigenvalues out, I want to just look at what the probabilities are, what the expectation value is, and then just look at a couple of base cases just to finish this argument off. So let me bring slides and some writing paper up. You'll remember we got at the end of the first half to this position where we had two eigenvalues, +1 and -1, which are pretty much what we would expect, because it doesn't really matter which way our spin's pointing. It's going to have the same angular momentum. And so if we measure it along z, it'll be +1 and -1. If we measure it along x, it'll be +1 and -1. If we measured it some direction in between, we would expect it to be +1 and -1. Of course, our eigenvectors now are a fair bit more complicated because they're not pointing along, a z or an x or a y. They're pointing in some arbitrary direction. And so what we get in here is trigonometric functions of some angle that tells us which direction that vector is pointing in this particular case. Okay, so you'll remember back on that slide, I had a spin in an arbitrary direction coming into the meter with spin and arbitrary detection as my measurement direction. And rather than do that problem in this second half, because the algebra would take us about an hour, I'm going to simplify that a little bit and just put a spin up in and measure some arbitrary direction. Okay, if you want to kick this one off to one side, I'll let you work on that. It's actually a really good exercise to do because you learn how to build up a bigger scale problem of a problem you're already familiar with. So what I'm going to do here is prepare a spin as spin up. And then I'm going to feed it into my meter. And I'm going to measure the component of the angular momentum along my n hat direction. Because that's basically the apparatus we just built, and that's what it's used for. Okay, so if we do that, we know that there's two possible outcomes. One is that we get +1, which is that the angular momentum component is aligned with the n hat vector. And the other is that we get -1, which is the angular momentum component is anti-aligned with the n hat vector. Okay, so let's work out the first one, p +1. This is going to be a projection operator problem, right? And so you'll remember what we do is we have our state on the outside. So this would be up here and up here. And then our projection operator is built with the basis state that we're interested in measuring. And in this particular case, because we're looking at the +1 eigenvalue here, we're looking at the λ1 eigenvector. So this will be λ1, λ1. I could go and build this up into a matrix and do it that way, and I'll do that in the second probability we do. The easier way to do this one in this particular case is just to take the inner product, u and λ1, and then multiply it by its complex conjugate, which is the same thing as taking the absolute value and squaring it. Okay, you'll know that from your complex maths lectures. This is one of these things where whether you do it by inner product or do it by projection operators depends on the problem. Okay, so as we've gone through some of the ones we've seen in lectures, it's been easier to do it by inner products, but you'll come up with some in your quizzes and assignments and exams and other questions that you do where actually it's easier to do it by setting up the outer product of the projection operator to get a matrix and work from there. Okay, so it's a good idea to know both because sometimes one's better than the other. So what we'll do here is do this. Our up vector here will be 1, 0. Our lambda 1 vector here will be cos theta on 2 sine theta on 2. Take the square here. And of course, when we do this product, 1 times cos theta over 2 plus 0 times sine theta over 2, what we're going to be left with is just a cos theta on 2 squared. And of course, the absolute value of cos takes care of itself, so it ends up being cos squared theta on 2 just here. Okay. And if you either remember back to the slide I had in the first half, or you have your notes beside you, you can look back and you'll see that that actually matches what we had in that first lecture as an expectation. The other thing that we can do here is get p of minus 1. And at this point, we know there's two ways to do this. The first is that we could take 1 minus p of plus 1, right? So this would simply be 1 minus cos squared theta over 2. You can take 1, break it up into sine squared theta over 2 plus cos squared theta on 2 minus cos squared theta on 2. These two terms cancel each other out, and what you're left with is sine squared theta on 2. Perfectly acceptable way to do it. And so the other way to do this would be to go p minus 1 just here. And this would be up, up. The projection operator we would use in this case would be for lambda 2. So we'd have lambda 2 in here. And what I'm going to do is actually do this by the full version with the matrix in it. Okay, so let's first get the projection operator. So lambda 2 is going to be, we've got minus sine theta on 2. So we're now using this vector here, cos theta on 2, minus sine theta on 2, cos theta on 2. And so this thing will give me a matrix where I get the top one and the top one for the top left element. So this will be sine squared theta on 2. The top right element is the top one and the right one. So this will be sine minus sine theta on 2 cos theta on 2. The bottom left will be the bottom and the left. So this will be minus sine theta on 2 cos theta on 2. And then the last one is right at the bottom. So this will be cos squared theta on 2, like so. And then my probability is going to look a little bit like this. What I will have is 1 and 0 as a row vector because it's a bra. I've got sine squared theta on 2 minus sine theta on 2 cos theta on 2 minus sine theta on 2 cos theta on 2. I'm just using shorthand here as S for sine and C for cos. Cos squared theta on 2. And over on here on the right hand side, we would have our vector for up 1, 0. And then, of course, we would do this multiplication here first. Okay, so we've got sine squared theta on 2 times 1 plus the little product on the right times 0. So that's going to give me 1, 0, and then a column vector here that will be sine squared theta on 2. And then the bottom row will come up. So the bottom element here would be minus sine theta on 2 cos theta on 2, like so. And then the last step is to do that product, okay? So this is now going to be 1 times sine squared theta plus 0 times sine cos. So it will be sine squared theta on 2, which is exactly the answer that we got up where we just took 1 minus the probability, okay? So you can see there that that's a little bit faster, but sometimes being able to do that matrix projection operator is not just really handy, but it's actually essential, okay? So it's really useful to know how to use it. So there's our two probabilities. And of course, we should know that P, the probability of plus 1 plus the probability of minus 1 should add to 1. And you know that because cos squared theta plus sine squared theta is equal to 1. All right, you can already see that in the algebras there. So the last thing to get to here is the expectation value. And in doing that, what I want to do here is actually start from the original definition of um, the expectation value as a probability weighted average of the measurable outcomes. I'm going to do that version in this lecture. And then if you want to try for yourselves what the bracket version of that was, which we saw a couple of lectures ago, you should get the same answer out. And I'll let you do that one as an exercise because that one takes a little bit more work and it's going to give you a good workout at doing sort of bracket version of expectation value. So this one here, the expectation value of sigma n is going to be essentially the sum of the eigenvalue, the eigenvalue times the probability of getting that eigenvalue. And in this case, it's actually pretty easy. It's going to be the probability of getting a +1 times +1 plus the probability of getting a -1 times -1, okay? So this is going to be +1 times cos squared theta on 2 minus or plus -1 times sine squared theta on 2. Okay, and you'll notice that I did a plus -1 there. This is me being cautious about my signs because the number of times in my past where I've been burned by racing my signs too fast is too many to count. So I kind of know sometimes when I just don't care and I just go fast, and then sometimes where I'm really careful about exactly what my sign is so I can make sure I get the right answer. It's the two banes of your existence as a physicist if you stick around long enough is sign errors and factors of 2. The pair of them will drive you crazy eventually. Okay, so what we've got here is cos squared theta on 2 minus sine squared theta on 2. Now, you'll remember here that we can go back to a relation that we had in our earlier work if we basically break this out. So what we can write this as is cos theta on 2 cos theta on 2 minus sine theta on 2 sine theta on 2. And I'm doing this explicitly because what I want to use here is the cos A cos B minus sine A sine B is equal to cos A plus B, okay? One thing to be aware of, and I used to keep this in my book of mathematical tricks, is to watch out for squares of cos functions because often the fact that they're appearing squared makes you forget that you can actually write them in the form that you've got here and use those sorts of relations to clean up the terms, okay? So what we would have here is actually cos of theta on 2 plus theta on 2, and this is just cos theta, which is exactly the value we had in the slide from lecture 1. Okay, pops out nice and easily. And as I mentioned earlier, I'll let you do the bracket version of that one just to keep the lectures on time. If you get stuck with it, come and ask me. I'm happy to help you out of that one. So where I want to finish off with this is to just look at some quickly along some cases of this, just to show that the values that we get for this general problem drop out to sensible values. And then the last thing I want to do is point out something called the spin polarization principle. I'm not going to prove it today, but I'm going to use it next week. So I want it in place for when I come to using it. So let's do the first thing, which is just to look at some limiting options for this particular case, right? And if you stick around in physics long enough, maybe you've even done it in first year a couple of times. Often what you do when you come up with something really general to test that everything's working properly, what you do is you stick a couple of what we call limiting cases or simple cases into it just to check that you get the right answer, right? So for example, we should be able to set our n to be along z, right? And if we do that, Our spin's pointing along z. Our n is at some angle theta to z. You'll remember we set that up in the first lecture. And so what we can do is we can put in the corresponding theta in there and just check that we get sensible results, right? So if our n was along z, then our theta would be equal to 0 degrees. If you don't see that immediately, pop back to the first lecture and have a look when we built that diagram of x and z, where we had nx, nz, and then we had n pointing along some direction. We defined theta to be relative to the z-axis, right? It's a very common convention in quantum mechanics to define everything, if you can, to the z-axis. It's kind of the preferred axis. So our p of plus 1 here would be equal to cos squared 0 on 2. And you know that that's going to be cos of 0, and cos of 0 is just 1, right? And 1 squared is 1, so that's just going to be 1. And then our probability of getting a minus 1 is going to be sine squared of 0 degrees on 2, which of course sine of 0 is 0, 0 squared is 0, okay? So all this is telling us is that if we set our measurement axis, we put a spin up in, if we set our measurement axis from some angle here to along z, we would expect to measure plus 1. We would absolutely not expect to measure down because we set it to up. And so those two probabilities come out consistent with that. And if we have a look at what the expectation value of n is now, it's going to be cos of theta, which is cos of 0 degrees. And of course, cos of 0 degrees is 1, right? And so all this is saying is that if we did a large enough series of measurements along here, we're always going to have spin up. So we're always going to get an up, right? And that's why the expectation value is plus 1. Okay, so let's consider another case now just to see if this works sensibly. What we should be able to do is set n along minus z, right? And so this would correspond to theta equals 180 degrees. What we're basically doing here is taking a spin up that we've set, and now we've got the arrow on our meter, or the magnetic field in our Stern-Gerlach experiment, pointing downwards instead, right? So this is kind of equivalent to thinking about it pointing, measuring up and putting it down in, right? So we're putting it up into something that's set to measure down. Here, our probability of plus 1 would be cos squared 180 degrees. And of course, you know that on 2. So 180 degrees on 2 is 90 degrees. Cos of 90 degrees is 0. 0 squared is 0, so this should be 0. The probability of getting a minus 1 here is going to be sine squared 180 degrees on 2. Of course, 180 degrees on 2 is 90. Sine of 90 is 1. 1 squared is 1, so it's 1. And our expectation value, sigma n, is going to be cos of 180 degrees. Getting a bit late at night now. Cos of 180 degrees, and of course we know for cos function it starts at 1, goes through 0 at 90, goes to minus 1 at 180 degrees, so this will be minus 1 just here. Okay, so we take our spin up, we got our meter set to measure spin down, and so what we will get is a minus 1 coming through because our spin is anti-aligned to our measurement axis, the same as when we were thinking about the other way around in putting it down into an up measurement axis in the first lecture. Okay, and of course the expectation value of minus 1 says that, you know, if we do a series of measurements, we always get minus 1, minus 1, minus 1, minus 1, so the average is minus 1. Okay, so the last one we can test that makes sense is n hat along our x-axis. And of course, if n hat's along our x-axis, where our theta is now 90 degrees, right? So we're putting a spin up, and we're basically asking, is the component of the angular momentum along x? So this would be theta equals 90 degrees just here. And so what we would have is p plus 1 equals cos squared 90 degrees on 2, okay? We know that 90 degrees on 2 is 45 degrees. Cos of 45 degrees is 1 over root 2, if I remember correctly. 1 over root 2 squared is a half. So this will be a half. And then our probability of a minus 1 here would be sine squared 90 degrees on 2. again, sine of 45 is 1 over root 2. 1 over root 2 squared is a half. This is a half here. So basically, if we have spin up, we put it into something that's measuring to the right, we would get 50-50 chance of spin pointing to the right and 50-50 chance of spin pointing to the left, 50% chance of spin pointing to the left. And then our expectation value, sigma n, is going to be cos of 90 degrees. And we know that cos curve goes from maximum through to negative. So the crossing point or 0 is at 90 degrees. So this will be 0. And basically what we'd have is 50% of the time it's up, 50% of the time to the right, 50% of the time to the left, and we add our plus 1, minus 1, plus 1, minus 1, add them all up over a statistical set, we would get an expectation value of 0, and sure enough, that's exactly what we get. Okay, so makes perfect sense all the way through here, what we get out of the values if we set n to specific directions. Okay. So the last point I want to pick up here is a thing called the spin polarization principle that basically follows off the back of this idea. And I'm not going to prove it because I don't have enough time in this lecture. I'm going to let you prove it for yourself as a bit of an exercise. And when we come back to it in lecture 8, I will use it for entangled spins. So you'll get to see how it gets used, but I don't want to do this simple case. So the spin polarization principle says that any state of a single spin is an eigenvector of some component of the spin. And what that really means is that for a spin pointing in any arbitrary direction I like, it could be up, it could be to the right, it could be at some angle, there will be some direction that I can find where the direction that I measure that state will be an eigenvector of that direction I measure. Okay, so what I'm really saying here is that for any given state A, there exists some direction n such that that state A is an eigenvector of the projection of the spin along that particular direction. What that means is that for any single spin, there's some orientation of the measurement axis where getting a +1 is guaranteed, right? And so there's sort of a consequence of that, which basically means that there's no state for a single spin for which the expectation values of all 3 components of the spin are 0. Okay, what this means is that if I've got a single spin, that spin has to point along some direction. And that means that if I work out what the expectation value is for the 3 different components, those have to be finite and end up adding to 1. And then specifically, they can't be 0. They can only be 0 if the spin doesn't exist anymore. Okay. The way we write that mathematically is either as the expectation value of the Pauli vector and the direction that you choose is equal to 1. Or another way to write this is as the sum of the squares of the Pauli of the expectation values of the Pauli matrix components in the 3 different directions. Okay, and so I'm going to leave this as an exercise for you to check for yourself. You can take a spin pointing in any direction you like, but actually the easiest way to do this is with an up or a down or a left or a right, and actually work through and prove for yourself that any particular state you want, you can start with ups and downs and lefts and rights, and then if you want, you can work up to building yourself arbitrary superpositions. Will obey this principle. Okay, it's a good chance for you to check for yourself that you can A, do expectation values well, B, basically be given, hey, prove such and such, and go through and do it. And you'll see this one come up again in lecture 8, where I'll do it for entangled spins, and you'll get to see how it works then if you want to give it a try now. And see what it looks like later. And so this is pretty much where we'll leave a single spin. And when we get to next week, we'll start talking about what happens when you have 2 spins and you start to do entanglement. I'll see you then.